All right, so this is the last section of notes here. This one is going to relate now to potential energy. So we've related this unit to dynamics with forces and gravity and tension. We related it obviously with kinematics. We had some kinematic stuff in there. And now we're going to relate this to energy. So we've talked about gravitational potential energy before. This is just mgh. But every time we've looked at this, we've always assumed my g value is 9.8. We've only dealt with gravitational potential energy from the surface of the Earth, or on the surface of the Earth. But g is not, obviously, constantly 9.8. So it depends on a couple of things. It depends on the mass of the planet. And distance from center. So these are the two things it depends on. So we can derive, what's that? From center, yeah. So we can derive a new equation when we're not on the surface of a planet. So from yesterday, we figured out that g m1 over r squared is my equation for g. And since this one is mgh, now we need to think, what mass am I dealing with here? Is it the mass of the planet, or is it the mass of whatever satellite we're dealing with? Satellite. So this would be mass 2. So plugging these two equations together, we're going to get this. No, I didn't show energy potential. So this is where the different things go with this. So here's your planet, here's your satellite. We're looking at different equations for this. So R for G is the distance between centers. From the center of the satellite to the center of my planet. That's what R is. H is the distance from where our 0 point is. Now we're always going to set our height in this case, or the reference point, from the center of the planet. That way, R is equal to H. So again, remember with potential energy, I can set my 0 point wherever I want. Right? If I look at everything on my desk, gravitational potential energy depends on, okay, is it from the desk? 0 potential energy. Is it from the ground? Okay, the height's from the ground. Or are we talking the height from the first floor? Then what's going to be the height from there? So it's all relative. So if I pick the H value to be relative to the center of the Earth, R and H are the same. And we're going to assume that. So here's our equation for this. I'll explain the negative in a sec. So that's what this whole thing's about. So what it says is, if you look at your formula sheet, you'll notice that there's a negative sign. So why do we do that? Whenever we talk about gravitational potential energy, we need a reference point, as we've seen. As this reference point, we will assign a gravitational potential energy of 0. So specifically in these cases, where we're going to set the 0 point, I just want to be grammatically correct. By second mass, we assign the 0 reference point when the distance between the objects is infinite. So if we've got infinite, I can't spell infinite, there we go. So that means whenever objects get closer together, potential energy is going to get smaller, right? So Remember, potential energy is how much potential does it have to do something. So the closer it is to the center of the object, the less potential energy it has. So this might be confusing, but essentially you can imagine something like this. If I've got, say, here's my planet, and an object that's infinite distance away, potential energy is 0. The closer and closer I get to the planet, potential energy gets smaller. So it goes from 0, it needs to get smaller, so it has to be negative. That's where that comes in. If we wanted to see what the graph looks like for this, so let's say this is my potential energy line, this is my radius. If at some distance far away, so basically at a far enough distance away, my potential energy is 0, and as I get closer to the object, I get bigger and bigger negative numbers. So this is what's going to happen. So as I get closer and closer, potential energy gets smaller. Same thing if I say, if I look at my pen above the desk. So if my 0 point's the desk, it has some potential energy. Potential energy gets smaller, 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 till it reaches 0. Yeah?
Why is it 0?
Because that's what we set it as. Yep. Because remember, we can pick the reference point. So I'm going to set it as 0. This is just conventionally what's done for that.
So you're setting the reference at the center of the planet or at the center of the
So we're setting the 0 point as an infinite distance away.
So at the center, or like wherever that object is.
Nope. Infinite away from the planet. So if we were talking about here's the planet, 0 point is as far away as you can get.
So it's not at the planet, it's away from.
Yeah. Yeah, and you'll see what this looks like once we get into some more questions. So let's give this a try. So we've got a satellite that's in orbit. We want to know what's the potential energy due to the gravitational force. So in this case, we use our new equation. This is this section where the equations start to get confusing, because notice sometimes we have r to the power of 1, sometimes we have r squared. So this is what's going to make it really confusing, and you need to really pay attention to your equations because this is not squared. So you need to make sure that you're aware which one's squared and which one's not. Yeah?
Is it not squared because you said h equals r and h to the power of 1 is r to the power of 2 and not with r to the power of 1?
Yeah. Yeah, so it just can't, the squared cancels out with the h. So with this, we know capital G, that's a constant. We know the two masses, one is the Earth, one is the satellite. The R value is not this. How come? This is not our R value.
I think it's a quarter.
No.
Because you have to add the distance to the center of the
Yeah.
Good. Yeah. So in this case, here's our planet, here's our satellite. We're told this distance is 3.6 times 10 to the 7. But we also need the radius of the Earth. Good. So as I mentioned yesterday, in yesterday's class, if you're going to make your own formula sheet, there's 4 variables you need to always include. You need the radius of the Earth, mass of the Earth, radius of the Moon, mass of the Moon. If I ask for any other planets, I will give those details to you. But those ones you for sure need to have. So to get the R in this case, it's going to be 3.6 times 10 to the 7. So this, plus the radius of the Earth. That's something you can just look up. It's 6.36 times 10 to the 6. I've got, 3.8. You're right. So you just add these two together, that gives you the radius. So plugging all those numbers in, negative 2.35 times 10 to the, my writing's really bad on this, 10. So negative potential energy, that's okay. You can have negative energies, and that's totally fine. Yeah.
The 6.38 is 1 gas.
No, the 6.38 is the radius of the Earth. Yep.
We're making the 0 point at an infinite distance. Doesn't that mean that H is no longer R? Because we're not making the 0 point at the center of the Earth.
Right. So we, that is a great question. You mean when we did this equation back here?
Yeah.
So the, that's a good question. I'm not actually sure right now. I'll look that up and then I'll let you know. I'm not sure. I do know that conventionally we've always set at an infinite distance as 0, and then all potential energies less than that have to be negative. But I forget the reasoning why in that case we set H equal to R, whereas when we deal with this we can't. I'll look that up. There is an explanation, I just don't know it right now. So note with this, the potential energy of this satellite relative to some position, infinite position, is negative. Meaning, so what does this mean? This means if I want to escape the Earth's gravity, I need to give more energy to the object. So that's what this means. The negative energy means in order to, let's say we want to launch a satellite that escapes Earth's gravity, we need to overcome whatever this potential energy is. But we'll have some more examples of that. So when we continue this question, doing the second part, what's the total energy of this satellite? So the satellite's in orbit at this specific distance. So we just figured out my potential energy is whatever's on the previous page, so negative 2.35 times 10 to the 10, right? Yep. Joules. If I want to figure out my total energy, it's going to be how much potential energy it has, plus however much kinetic energy it has. The printer prints it out funny, so you'd skip that page and then the next page should be the one we're on, yeah. Yeah, somehow when I printed it out, it skipped this page entirely and moved on to the next one, so I had to go back and staple it in.
We're not going to use the table.
Next. It's just these two pages are flipped. So all I need to do is figure out what's the kinetic energy of our satellite. So if I want kinetic energy, energy kinetic is equal to a half mv squared. I have the mass of the satellite. I'm just missing what the speed is. So I have this, it's 2,500. How could I get the speed? Yeah, so we're going to use stuff that you previously saw. So actually using what was done yesterday, we have this other equation. We've got that acceleration centripetal equals the acceleration due to gravity. From this, because AC depends on the speed, we can figure this out. So this is v squared over r is equal to gm1 over r squared. And these ones we all know. V we're looking for. R's, I can actually cancel out the squared with one of those R's. Capital G we know. Mass of the Earth we know. We just figured out the R. We know the distance between the center of the Earth to where our satellite is. So you can solve for V. (3068). Like always, I'm skipping all the algebra and putting in the numbers. That part I think you can get. Now that I have my V, I've got the speed, I can put that into EK, and then I've got my two energies. So from here, it's pretty straightforward. So plug in my speed, 3068, square that. We're going to have a rather large number of 1.176. Oops, 10. We got EK. Now I add the EP and the EK so that I get a total energy of negative 1.17 times 10 to the 10, right? Yeah, 10. So this is the total amount of energy that this object has while it's in orbit. This is a very common kind of question, just so that you're aware. These are the nice 10-point questions, or 7-point questions, where I ask you what's the total energy of a satellite. You need to figure out first what's EP, then what's EK. It's got a whole bunch of steps. This is perfect for a long answer question. Yeah.
So in space, any object only has the potential energy, kinetic energy, as energy that doesn't have to be.
Yeah, we're going to ignore all the other types of energy. We're just going to deal with potential and kinetic. Unless, ooh, that would be a fun question. We can have an object that's dropped, and then as it enters the Earth's atmosphere, you could lose heat. That'd be nice. And then what speed does it hit the ground at? So I could give you something like that. But then I would tell you that there's heat. I forget if I actually give you that, but it would be a nice question to give you. Change in potential energy. What time do we got? 55, okay. So change in potential energy, we've seen something like this before. This is also equal to work done on an object. So change in EP is equal to the final potential energy minus the initial. But because of the negative signs, we can change this equation a little bit. So we could say that change in EP, we can plug in our values here. So negative gm1, m2 over r final minus negative gm1, m2 over r initial. So we can rearrange this equation because these are both positive. They cancel out. We can rearrange this as g m1, m2 over r initial minus g m1, m2 over r final. And even this is a really long equation to put into your calculator, so why not make this even easier for ourselves? Both of these have g m1, m2, so let's just factor it out. Then you don't have to write it twice, and you just go 1 over ri minus 1 over rf. So here is a derived equation that will make your life a little bit easier if you want to put this in. This is not obviously a fundamental equation because it's just a derivation of something that you know. So if you don't have this on your formula sheet, it's not the end of the world, but this can and will make your lives a little bit easier if you're dealing with change of potential energy, or work, because work is change in energy. Yeah.
If I just decide to do the long way,
Yeah. Yep, that's exactly what I said. So you don't have to know this, it's just a useful derivation. It can make your life easier.
So wait, it doesn't work in all cases?
No, it does work in all cases. Yep.
Are we allowed to put derivations on our function?
Derivations?
Like the very last problem?
Yeah. Yeah, you can, any formula you're allowed to put on your sheet, that's totally fine.
Can I do by plugging in numbers or do I have to, like, can I guess the numbers?
No, you need to measure everything. So here's where work comes into play. So how much work is required to move a satellite from an orbital radius of 1.8 times 10 to the 7 meters to a radius of 4.2 times 10 to the 7 meters? So work, change in energy, and what type of energy am I changing in this case? Just potential. So this is like the ones where I'm lifting a box and moving it up a certain amount. How much work am I doing? It doesn't talk about a change in the speed in this case. So this is, I'm going to move this over here. We have a nice, handy, useful equation we just derived. I'm going to assume this is Earth. It doesn't say Earth. Let's assume it's Earth. We have everything. G we know, mass of the Earth we know, mass of the satellite we know, we have our initial, we have our final. So it's just as simple as typing it in. Be careful when you're putting the 1 over the this kind of an expression, just to make sure it's actually calculating it correctly. I'm just going to show you the answer for the sake of time. This is how much work it requires to move a satellite. So it's positive because you need to actually do work to move the object. It's hard to put a satellite farther away from the Earth because gravity wants to pull it down. If you were, notice if we were to take it from a further radius to a shorter radius, the work would be negative because you don't have to put in work, you actually have to take out energy with that. You don't have to remember if it would be positive or negative. It will come out based on this. Questions with this? Ooh, this is like the question that we just talked about. Although this one says ignore air friction. So that means we're not going to deal with heat loss. So let's suppose the International Space Station drops a waste shuttle from this specific altitude. We want to know at what speed would it hit the Earth if there's no air friction, which obviously is not true, but let's just assume it. So what's going on here? I'm going to have a change in kinetic. What else? I'm going to have a change in both, right? Because not only am I changing height, I'm going to change speed. So I need to deal a bit with both. So in this case, we've got our box starts here. It's going to fall down and land here. So this is my R initial. This is my R final. Just to compare between the two. They like to trick you with the altitude question. If this is my altitude, then I need to add the radius of the Earth to this. So just make sure you read the question carefully. So my R initial is going to be this 3.5 times 10 to the 5 plus radius of the Earth. And then obviously RF is going to be the radius of the Earth. So there's an equation that we used, not as frequently, but we used it a bit. with conservation of energy. I don't know if you remember this one. That's a K. Does this ring a bell? So this is basically the conservation of energy just rearranged into change in different EPs. So this is convenient because we can calculate change in EP in one equation, and that's going to equal negative of EK. And then this is going to be how we're going to go about solving this. If you wanted to, you could use your regular old conservation of energy, energy initial kinetic plus energy initial potential equals the final energies. If you wanted to do it that way, that's fine. That could work. This is just going to make our lives a little bit easier. So change in EP, we have this equation. We have this. I've got G. I have M1, right, mass of the Earth. M2, I've got the waste shuttle. I have my two radiuses. So I've got Ri, is this plus the radius of the Earth. I've got Rf, this one equals the radius of the Earth. So you can plug those numbers in. So this would give me negative 8.128 times 10 to the 8 joules. So from this, I can figure out change in EK. We have this expression. So change in EK simply equal to negative change in EP, which is therefore positive 8.128 times 10 to the 8 joules. Any guesses where I'm going to go from there? Yeah, so I have a change in kinetic energy. I want what's the final speed. So just simply looking at, okay, now we know change in EK. So change in EK is equal to EK final minus EK initial. What's my EK initial? 0. I start at rest. So therefore, change in EK is equal to a half m. I'll write m2 just so we are clear. It's the satellite VF squared. I have change in EK. I have the mass of the satellite. I can solve for VF. Doing all this, we get this. So the question I'm doing here in the notes, these ones are very common to what you will see in the practice problems and on the test. These are very common types of questions. So the questions of what's the total energy? Assume this is dropped in space. What's the final speed? I could do the reverse of that. What speed would I need to launch something to get it into a specific orbit? Which again is just using the same method, just in the reverse. So you can see these are the typical types of questions, just so you're aware of that. Yeah?
Why do we use the mass of the satellite?
Because this is the kinetic energy of the satellite, not the kinetic energy of the planet.
Will we ever use the kinetic energy of the planet?
Only if the planet is the one that's in orbit around something else. Well, the Earth orbits around the sun, so it could happen. Any other questions with this one, or the methodology of how I did this one?
So we have cases where the kinetic energy initial is not zero.
Mm-hmm. Yep. But I mean, if there will be cases where this is not 0, and then you just have a minus half mvi squared.
And we'll be given the
Yep. Yep. You'll either be given the vi, or you'll have to solve it. One last thing. A very special case that is going to be often enough seen that it's worth going over. So what goes up must come down. Unless you throw it really hard, then it'll escape the Earth's gravity. So escape velocity is a specific term that is used for what's the minimum velocity you give an object in order for it to break free of Earth's gravity. So if you can throw something up at this speed, it's going to escape Earth's gravity. Something that's handy to know. So notice this is the minimum speed, so meaning anything above that, it will escape. So basically what we're going to need to do is we're going to give an object enough kinetic energy in order to match its potential energy once it gets to infinity. So let's look at what this would look like. So essentially we've got this. Here's a planet. Here's our little satellite. And we want to do is launch it at some V escape. So that what's going to happen is eventually it reaches some point here where your potential energy is 0.
It only escapes out of Earth's gravity when it's at an infinite distance.
Yes. Infinite being a relative term. But yes. So in this case, what we wanted to do is we want this, if we want the minimum, we give this just enough kinetic energy so that it reaches this point and our kinetic energy is 0. If it's going to be the minimum, it's just going to reach that edge point and come to a stop. So we know what the end positions are, we just don't know what this is going to be. We don't know what EK initial is. We don't know what EP initial is. Depending on the planet, we can figure those out. But this is what we need to deal with. So we can derive an equation with this. And I'll do that on the side here so you can see where it comes from. So we've got this equation, change in EK equals negative change in EP. So this is EK final minus EK initial equals negative EP final minus EP initial. If we look at our finals, they're both 0. We want EP final to be 0. We want EK final to be 0. So what I'm left with is negative EKI equals, negative and negative cancel out, so we get positive EPI. Have I lost anyone at this point?
No.
Good. We want to know what EKI is, or what's the initial speed, so let's put in some equations here. So negative half mvi squared equals the equation for EPI, which is negative g m1 m2 over r. I've got a mass on the left-hand side. Is that mass 1 or mass 2? Why would you say mass 2? Exactly. So the kinetic energy here is of the object. So therefore it has to be the mass of the object. So this is mass 2, and these cancel. Both sides are negative, those cancel. So let's go about figuring this out. Solve for VI, and then we get VI equals, let's see, times that, so 2 GM1 over R. Take the square root. So from this bit of information, we can now create a V-escape equation, escape velocity equation. So V-escape equals the square root of 2g m1, whatever the mass of the planet is, divided by r, and specifically this is the initial radius. Wherever I am in position to the planet, that's ri. So again, the derivation you don't need to know. You don't have to write, you don't need to write that on your formula sheet. I'm not going to ask for any derivations, but it's just interesting to see where that comes from. And notice V-escape depends really only on two things. It depends on the mass of the planet, and it depends on the radius that it starts at. So whether you are throwing a rock or launching a satellite, same V-escape. Mm-hmm. Yeah? Yeah, so once it reaches this final point, it just stops. Yeah. So this equation is really easy. So if I give you a question, what speed do you need to throw something to get out of Earth's gravitational pull? You just use this equation. You can put that on your formula sheet, you're good. So V escape is square root of 2 times g times the mass of the planet, which in this case is Earth, over the initial radius. So we're going to assume we're on the surface of the planet because it doesn't tell us anything else. Plug in your numbers. 1.1 times 10 to the 4 meters per second. So any object on the Earth's surface, if you wanted to escape the gravitational pull, throw it at this speed, which is fairly fast. I kind of gave this away already. Does the mass of the rock matter? No. No, doesn't matter. But if I wanted to have a bigger object to throw upwards, I would need to give it a bigger amount of energy. So even though the mass itself doesn't matter, if I wanted to figure out how much energy do I need to launch something at, I would have a bigger amount of energy. So yes, it does take more energy to get something up, but the velocity doesn't matter.
Do they actually launch rockets?
No, this is assuming there's no air friction. Yeah, so this is again in our idealistic high school physics mode.
And why would you do that?
Yeah.
So ideally, an object can't reach that infinite point. Like we haven't done it.
So the problem with trying to reach an infinite point like this is the fact that, okay, essentially you don't escape the gravity of a planet. You can get so far that you don't experience the gravity, but the problem is then you're dealing with the gravitational pull of other things. Because this is assuming that there's no other forces or gravitational pulls that are affecting the object. When in reality, between the planet and an infinite distance, there's a bunch of other pulls that are going to occur on that satellite. Hopefully in all this physics that you're learning in high school, you realize just how complicated physics can get once you stop assuming things. If you're trying to do as accurate as a representation as you want for, say, landing something on the moon, it's way more complicated than just what we see here. So that is the last section of this unit.